Hey everyone, in this video we're going to continue our discussion of concavity, how the second derivative affects the shape of the graph of the function. So let's look at this function. We have g of t equals 8t minus 2 tangent of t on 0 to 2 pi. So we want to determine the intervals where the function is increasing and decreasing, and then where the function is concave up or concave down. So the first one, that means we want the first derivative. So we want to find g prime of t. And for the second one, we're going to want to find the second derivative. So let's start with part A, finding the intervals where the function is increasing or decreasing. So we need to find g prime, the first derivative, and then set the derivative equal to 0 to find critical numbers. So what is the derivative of that function? So g prime is going to be 8, right? The derivative of 8t is 8 minus the derivative of tangent is secant square. So I'm going to have 2 secant square of t. And so that's the derivative. Now we set it equal to 0 and solve for t. And to find critical numbers, now remember, critical numbers are where the function, where the derivative is 0 or undefined. I guess we're using a t. So wherever the function is 0 or undefined, the derivative of the function. Then this we set equal to 0, but notice that here, right, but we don't have a denominator, but we have to think about, since I have a trig function, I have secant, it's a reciprocal. So where is secant undefined? So this function I have to look at a little bit more into also kind of the domain of the function, but here, just the derivative, where is secant undefined? Secant is undefined when cosine is 0, right? Because secant of t is 1 over cosine. So where does this happen? This happens at pi over 2 and 3 pi over 2 on the interval. We're only on the interval 0 to 2 pi. And so if as an interval was not specified, then I will have to say pi over 2 plus pi n, right? All the multiples of pi over 2. But here we're just looking at between 0 and 2 pi. So these are going to be critical numbers because that's where secant is undefined, right? Secant square is really secant of t and then quantity square. So it's really wherever secant is undefined. So those are going to be critical numbers. And then now let's solve for the ones where the derivative is 0. So pi over 2 and 3 pi over 2 are where the derivative is undefined because secant is undefined there. So now let's find the ones where the derivative is 0. So solve for t. So I'm going to move the secant over to the other side. And then divide by 2. So I have 4 equals secant square of t. Take the square root of both sides. So I'm going to have secant of t equals to plus or minus 2, right? Anytime you take the square root of something with a variable, you gain that plus or minus. So when is secant equal to 2, or another way you can think of it is secant is 1 over cosine. And so you can say, okay, so when is cosine of t equal to plus or minus 1/2? And so this gives us our pi over 6's and pi over 3's. So which one is our reference angle? Is it pi over 6 or pi over 3? And so depending on how you remember your sines and cosines, I tend to use this little guy. So 0, 6, 4, 3, 2, those are my angles. 0, pi over 6, pi over 4, pi over 3, pi over 2. Sine of 0 is 0. So cosine to be 1/2, then I'm looking at cosine, so it's over here, and so it'll be the pi over 3's will be my reference angle. So cosine is, let me split this up. Cosine is positive 1/2 in what quadrants? So cosine is positive in quadrant 1 and quadrant 4. So that means t is going to be pi over 3, that's the one in quadrant 1, and what's the one in quadrant 4? It will be, let's see, 4 pi over 3, so 5 pi over 3. And then the other ones will be when cosine of t equals negative 1/2. So this will put us in quadrant 2 and quadrant 3. So then t will be 2 pi over 3 and 4 pi over 3. So essentially all the pi over 3's from between 0 and 2 pi. So our critical numbers are, starting from the smallest one, so pi over 3, then pi over 2, that's where the derivative is undefined, then 2 pi over 3, 4 pi over 3, then 3 pi over 2, where the derivative is undefined, and then 5 pi over 3. So these are our critical numbers, right? So here, these two are from g prime being undefined, and the other ones are where g prime is 0. So we have 6 critical numbers, and so now we can draw our number line and put them in here. So starting with our pi over 3, then pi over 2, so this is creating our different intervals. And then what's the next one? 2 pi over 3, then 4 pi over 3, 3 pi over 2, and 5 pi over 3. 6 of them, okay. And so we want to test the first derivative, so g prime of t, and we want to see what is the function doing. What is g of t doing? So I have from 0 to pi over 3 to test. And so here, let's see, the derivative is 0 there, undefined there, 0 there, 0 there, undefined there, and 0 there. And so now you want to pick values in between these to test. So let's look at our different test points. So between 0 and pi over 3, 0 is included, so we can just plug in 0 and see what we get, or you could try pi over 6. So let's say t equals pi over 6 for the first one, and we're trying it into the first derivative. So what is our first derivative? It is, where did we find it? 8 minus 2 secant square of t. So that is what our derivative is, right? So g prime of t is 8 minus secant of t, I'm going to do it this way, square. So when you have t equals pi over 6, what's g prime of pi over 6? So it'll be 8 minus secant of pi over 6 square. So this is going to be, what's secant of pi over 6? Well, we know it's going to be 2, right? Because that came from a critical number. So 2 square is 4, so 8 minus 4 is positive. So then I know that from this interval, I'm going to have the derivative is positive, which means that the function is increasing. Now between pi over 3 and pi over 2, what angle could you pick? We're looking at the interval between pi over 3 and pi over 2. And so what angle could you pick there? You could try to maybe convert it to degrees and use your calculator to figure out what you could do. So let's see, on the interval pi over 3 to pi over 2, right, that's 60 degrees and this is 90 degrees. So you could pick like 80 degrees, or you could also pick to be the midpoint between these two. So where's the midpoint of pi over 3 and pi over 2? So add them up and divide by 2. So when you add them up, you get 5 pi over 6, and then divide by 2, right, the average, the midpoint, and then you're going to get 5 pi over 12. And so you could test that. So g prime of 5 pi over 12 will be 8 minus secant of 5 pi over 12 squared. And you put that on a calculator, and now you're going to get this value is going to be larger than 8. So it's going to give you a negative. So the derivative here is negative, which means that the function is decreasing. Now what about between pi over 2 and 2 pi over 3? So you could again change it to degrees and say between 90 and 120. So you could pick 100 degrees and just in your calculator make sure that you're in degree mode when you do 8 minus secant of 100 degrees square. Or again, you could try to do the midpoint. So when you're between pi over 2 and 2 pi over 3, the midpoint of that is going to be, so add them up, so pi over 2 plus 2 pi over 3, that's going to give you, what, 7 pi over 6, and then when you divide it by 2 to get the midpoint, will be 7 pi over 12. And so you'll have g prime of 7 pi over 12 is 8 minus secant of 7 pi over 12 squared. Or you can use, like I said, you can use degrees. Change them to degrees, 90, 120, pick something in between if you don't want to try to find the midpoint with the fractions there. But when you do this, you're going to get that secant of 7 pi over 12, that's still a positive number. Square is going to be bigger than 8, so you're still going to get a negative here for this derivative. And so that means the derivative here is negative, which means that the function continues to decrease. Which makes sense because at pi over 2, this is undefined. And notice that the function itself is tangent, and tangent is sine over cosine. So this is going to have, we're going to have asymptotes at pi over 2 and 3 pi over 2 because the function itself is undefined there. So you have vertical asymptotes at those values. So that makes sense, at least, that there's no critical number, no max or min there. And then continue on checking your test points for the rest of the intervals. So what about between 2 pi over 3 and 4 pi over 3? Right, what value of t could you pick? And this one's a little nicer because this is when you make the transition from the third quadrant to the fourth quadrant, so you can nicely choose pi as your test point. So g prime of pi, which is going to be 8 minus secant of pi squared. And secant of pi is -1, so this is now going to be 8 minus 1, right? -1 square is 1, so you're going to come back to a positive. So the derivative here is going to be positive, which means that the function is increasing. And so I'll let you do these ones. So what happens on those? And once you have your test points for that and you check them, you can write, then we can say the function is increasing on what intervals? On, and then let's go look at our number line. So it's increasing on 0 to pi over 3, and we should probably truncate it so that we don't say negative infinity, right? We are starting at 0 and we are ending at 2 pi. So it'll be from 0 to pi over 3 is where the derivative is positive, and then 2 pi over 3 to 4 pi over 3, and then what happens on the other ones. So keep going with your testing of the critical numbers, and so we can say this is increasing from 0 to pi over 3, union 2 pi over 3 to 4 pi over 3, and there's probably one more. So what's the other one? And the function is decreasing on the ones where the derivative is negative. So that was, and then go back to your number line, or if you use the table of values. But when you're doing a quiz or a test, like I want to see either the number line or the table with the intervals and your test point and checking the first derivative or the second derivative, whichever one you're doing. And so here the decreasing is pi over 3 to pi over 2. This is undefined, so we have to then jump to pi over 2 to 2 pi over 3, and then what else happens over here. And so that's how you will list your intervals. And so from here we can see we have a local max at pi over 3. That's where it occurs. the value will be, plug it into the original function, and then you have a local min here at 2 pi over 3, and then what happens at 4 pi over 3? Right, you're going to have a local max, or is it a saddle? And then what happens at 5 pi over 3? So the ones where the derivative is 0, those are potentially where we're going to have local extrema or saddle points. And so we can start listing our decreasing. So we can say pi over 3 to pi over 2, union, pi over 2 to 2 pi over 3, union, and then finish it off with, after you do the test points for the 3 remaining little intervals. All right, so that's where the function is increasing and decreasing. Now what about concavity? The curvature of the function. So part B, where's the function concave up or concave down? So let's remind ourselves that our derivative was 8 minus secant square of t. Sorry, minus 2 secant square of t. So, oh, I wrote it wrong here, but I don't think that changed too much. These values should still come out to be the way that they are, positive, negative, negative, positive. All right, so now I want to take the second derivative, so g prime of t. Let me rewrite it as 8 minus 2 secant of t squared, so that I can use the chain rule. In order to take the derivative here, I need the chain rule. And so now the second derivative is that 0, and bring the power down, so I'm going to have minus 4, the inside stays the same, then times the derivative of the inside. The derivative of secant is secant tangent. And so we can say then the second derivative is negative 4 tangent of t times secant square of t, and set that equal to 0 to find your candidates for inflection points. So when I set this equal to 0, is either tangent is 0 or secant square of t is 0. We can also try to rewrite it in terms of sines and cosines. So tangent is sine over cosine, and secant square is 1 over cosine square of t. And so then this becomes what? Negative 4 sine t over cosine times cosine square is cosine cube of t. And set that equal to 0. And so now it's easier to see we have a fraction. So this is going to be, the derivative is 0 when the numerator is 0, and it's undefined when the denominator is 0. So where is sine of t equal to 0? Sine of t is 0 when t is 0, pi, and 2 pi on the interval from 0 to 2 pi. And cosine of t, cosine cube, but that just really means cosine of t is 0 when t is pi over 2 and 3 pi over 2. And so those now become our critical numbers. And so let's do the number line again, but now we are testing the second derivative. So I'm going to, because I'm confined to the interval 0 to 2 pi, and then we're going to put in our critical numbers in order. So pi over 2, pi, 3 pi over 2, and 2 pi. And we are testing the second derivative. So g double prime is negative 4 sine t over cosine cube of t. Make sure I've written it correctly this time. And so now let's pick test points. And we're checking now the second derivative and seeing what does that mean about the function, the original function. So our test points between 0 and pi over 2, you can pick pi over 4. So let t be pi over 4, and so put it in here. What do we get. So you're going to have -4 times the sine of pi over 4, which this is in the first quadrant, so sine of in the first quadrant is positive, and then cosine of pi over 4, again in the first quadrant, so that's positive, and positive cube remains positive. So you have a -4 times positive is going to be negative. So the second derivative is negative. What does that mean about the function? It's curving which way? Happy face or sad face? Upwards or downwards? So this is because the second derivative is negative, is curving downwards. So we're concave down. And then what about between pi over 2 and pi? You can pick the other pi over 4. So you can say 3 pi over 4, just because those values are nice, right? So you're going to have -4 times sine of 3 pi over 4. That's in the second quadrant, so that's still going to be positive, divided by cosine cube of 3 pi over 4. Now cosine in the second quadrant is negative, so a negative to the odd power to the third is still negative. So now you have negative times positive divided by negative, so that's positive. So second derivative is positive, means that the function is curving upwards, concave up. So at pi over 2, we do have a point of inflection. Concavity does change, and the second derivative here is, oh wait, see, this is why it's important to write what happens to the derivative. So it's 0 at 0 pi and 2 pi, but it's undefined at pi over 2 and 3 pi over 2. So do we have an inflection point there? No, right? Because the derivative here is actually undefined. So it's 0 at pi and at 2 pi and at 0, but it's undefined at those. So actually the concavity does change, but because pi over 2 and 3 pi over 2 are not in the domain, that's not an inflection point. So an example of why knowing the domain of your function is really important. All right, so let's keep going. So something between pi and 3 pi over 2, you can pick the next pi over 4. So pick t equals to 5 pi over 4. And so you're going to have -4 times sine of 5 pi over 4. Now you're in the third quadrant, so sine is negative and cosine remains negative, and negative cube is negative. So now you're going to have negative times a negative is positive, divided by negative is negative. So in this interval, we're going to have second derivative is negative, which means the function is concave down. Now that is an inflection point because the second derivative is 0 there, and concavity did change. So now that's a point of inflection. 3 pi over 2, even if concavity changes, that's not gonna be an inflection point, but we do want the intervals. So pick t equals the next pi over 4. So do 7 pi over 4. And so you're gonna have -4 times sine of 7 pi over 4. This is in the fourth quadrant, so sine there is negative, divided by cosine of pi over 4. In the fourth quadrant, cosine is positive. So you're going to have positive to the third power, remains positive, negative times a negative is positive. So it's positive there, which means the function is concave up. So concavity does change at a few places, but we only have one inflection point where the second derivative is 0 and concavity did change. Right, concavity changed here, but these are not in the domain of the function, so I won't be able to find a y value corresponding to these, so I can't call them inflection points. All right, so now we can say the function is concave up on where? Pi over 2 to pi and 3 pi over 2 to 2 pi. And then it's concave down on 0 to pi over 2 and pi to 3 pi over 2. So you will list those intervals as the places where the function is concave up and concave down. So showing either a number line or a table of values like the book does will be really important, as that's part of showing your work. Just taking the derivative and listing the intervals is not going to earn you points on quizzes and exams. So make sure that you get really familiar with either this number line method or the way that the book does it, which is how I started to do it in the prior videos when we did the first derivative test, is how with the table of values. So I was doing both. I was doing a table of values with the intervals, the test point, and the result of the derivative, and I was doing the number line at the same time. So either of those will work in terms of showing your work. And let's see, the last thing is the second derivative test, which is to check if a critical number is a maximum or a minimum. You can use the second derivative. So going back up here to determine, right, if something is a local max or a local min, I can use the second derivative. So let me go to one that we didn't finish because this is just a lot of work, right? So make sure that you give yourself plenty of time to start the homework, because as you can see, one problem is taking us 25 minutes to do. Although I am talking a lot, but just be aware of that. Don't leave your homework to the day that is due, because then it's going to feel overwhelming. All right, so let's say I already know that that's a local max and that's a local min. We don't know about 4 pi over 3 or 5 pi over 3. So these are critical numbers from the first derivative. So I want to see if these are local max or local mins. So I can use my second derivative to test them. And so this is what we're going to do. So I'll write it out down here. So what the second derivative test really says is that if you have a critical number from the first derivative, so if C is a critical number where the first derivative is 0, then C is a local maximum if the second derivative evaluated as C is less than 0. So what does less than 0 mean? That it's negative. So if it's negative, that means it's concave down, right? So that means that at C, you're having this. So that creates a local max. So that's how the second derivative test works. And C is a local minimum if, what do you think? If the second derivative is positive. Right, and so that means, because if the second derivative is positive, that means that you're concave up, so evaluated at C. So that means that when it's concave up, you look like that at C, so then you have a local min. So that's what the second derivative test says. So going back to our example where we had g prime of x was r of t, which was 8 minus 2 secant square of t, we got critical numbers. We had a bunch. What were they? It was pi over 3, 2 pi over 3, 4 pi over 3, all the pi over 3s, and 5 pi over 3. So from the number line above, we already saw that pi over 3 and 2 pi over 3, what they were. So let's focus on 4 pi over 3, since we didn't know what that was. Is it a local max or is it a local min? So our second derivative, we had found it to be, what was it? We had negative 4 sine t over cosine cube of t, if I remember correctly. We should probably double check. I want to make sure I don't make any algebra mistakes here. So yes. So that is our second derivative. So what the second derivative test then says is that you can take a critical number from the first derivative and plug it into the second derivative. So if I say g double prime of 4 pi over 3, this is going to be, and I'm looking for the value, is it going to be positive or negative? So this is going to be negative 4 sine of 4 pi over 3 over cosine of 4 pi over 3 to the third, cosine cube. So 4 pi over 3 is an angle that is in the third quadrant, so sine is negative there. So this is negative, and 4 pi over 3 still in the third quadrant, so this is also negative, and negative cube is negative. So you have the second derivative of 4 pi over 3 is you have the negative 4 times a negative times a negative, so which is negative. So that means the second derivative is negative when I evaluate the critical number. So that means at that critical number, I have a local max. So I can say, therefore, t equals 4 pi over 3 yields a local max. Right? If the second derivative is negative, that means it's concave down. So at C, at 4 pi over 3, would look like that. So you have a maximum value there. How do you find the value? Plug it into the original function. So g of t at 4 pi over 3, this will give you the y value. So the original function was 8t minus 2 tangent of t. So this will be 8 times 4 pi over 3 minus 2 tangent of 4 pi over 3. So this will be the y value associated with that local max. So you're going to have a local maximum will be y equals whatever this is. So 8 times 4, so 32 pi over 3 minus 2 times tangent of 4 pi over 3. Now remember, the 4 pi over 3 is in the third quadrant, so tangent there is positive, right? So then this will be, our reference angle is pi over 3, so tangent is root 3. And because we're in the third quadrant, it's positive, so 2 root 3. Since sine and cosine are both negative in the third quadrant, then sine over cosine is positive. And so this will be your y value. So you will have a local max will be the point, the x value or t value, 4 pi over 3, and the y value will be this, which is not very nice to write. So that will be the local max. Now this is not an absolute max, even though now we are on a closed interval 0 to 2 pi, you could find the absolute value, maximum value. But this is just how you find a local max. So to determine if a critical number is a max or a min, you can take the second derivative and just plug in your critical numbers into the second derivative and see. And what the second derivative tells us is that if the second derivative is negative, then that critical number gives you a local max. If the second derivative is positive, then that critical number gives you a local min. And that is a nice little shortcut for determining if you're just asked to find local maxes and local mins without having to go through the entire number line process to see, okay, is it, or where's the first derivative one? To see whether it's increasing and then decreasing, right? And then plugging it into the second derivative is just creates a shortcut, other than the fact that you have to take the second derivative. So depending, I guess, on how easy or how simple it is to take the second derivative, that may be the way to go. If taking the second derivative involves an extensive, say, quotient rule with embedded chain rules, I might just opt for doing the number line to see increasing to decreasing, oh, that's a local max, instead of putting out the work and finding the second derivative. But if I have to determine concavity anyway, just might as well take the first derivative, second derivative, and do it that way. So, all right, email me if you have any questions.